a lot of questions as well, a lot of things to discuss. Let me see. Actually, it might be easier if I just share part of the browser. Right, this is probably gonna work. So I did a further experiments on the return normalization. A couple different ways to try it. Like basically, I set it to reset the filter, reset the return filter, and whether to reset the it's not right. It's a running stats reset, not running state reset. So I did an experimenting with those, and this is the result you see. I ran them on two environments. I think the first one is a humanoid, and the second one is a walker. And then the humanoid example, the best performing one really is having the return filter reset as well as the running stat reset. And then I think it's also the same on the second example with the walker as well, but their performance all kind of degrade. I didn't have a lot of time investigating into the reason why their performances is so bad, but this week I was again kind of busy with the research work. I was being distracted by a bug that I was having, which I can gladly share with you guys. It's actually quite an interesting bug, and the way that I solve it is kind of interesting as well. But probably, Rosalind, you should do the presentations on what you did first, and then maybe we can get into it.
Before, a quick question. When you say return normalization, is it really the return or the reward normalization? Because in the source code there is actually two versions.
Yes, so the one that I'm using is the return normalization. So it's a reward filter instead of the Z filter, in other words.
Really?
Yeah.
And it works?
To an extent. Like you see that the performance degrades so badly in the end, right? It's the reward filter. And then as you can see, it's using the reward filter, and it really depends on whether you reset it or not, right? So this is basically the two arguments that's controlling everything. So if the return filter reset, then the reward filter reset, and I have to write an extra method called the running stat reset. So what that basically does is that I just initialize a new instance of the running stat instead of keeping what was already there.
I see. Because wait, I will share my screen.
Go ahead.
And in actually the source code itself. Okay.
Take your time.
I actually have to disable. Okay. Here in the torch utils, where they provide the reward filter, there's actually this comment which says incorrect reward normalization.
Yeah, I would. Go ahead.
But that's the one you're using, right?
Yeah, and apparently that's the one that they are using by default.
By default too.
And I actually go ahead.
No, because in the paper, I think they have. It's instead written reward normalization instead of return. So just using the Z filter, basically. And actually, in my case, that's what gives a good performance.
Wait, so did you say that they use the reward normalization by default instead of the
Yes,
return?
here, well, at least it's written norm rewards. So
Yeah, I don't know about that. So there's something further that I can show you. That may be different. Oh, can you go back to the formula over there?
this one?
Yeah, yeah. So this is, let me see. So why would I say scale observation?
I think they consider it as a generic function.
Oh,
so
okay.
just scale, maybe statistic instead.
Right. So in this case, they are using the return normalization, right?
Yes, the weirdly backward normalized return, indeed.
Uh-huh. Right. Backwards normally. Right. So if you take a look at my screen, I actually raised an issue to their GitHub repo, but so far no one has said anything yet. Yeah, I said the same thing. The comment suggests it uses incorrect reward normalization. What do you mean? But in the default one, so they have a script that sort of gets you to set up everything. And that script by default uses the return filter. Like if you see here, cd source.
Okay, I think I understand.
So you see they use returns by default.
Returns. Yes. It activates the reward filter instead of set.
Yeah, instead of z filter, exactly. So that was an issue.
Fair enough.
Yeah, but yeah, what's the experiments that you have conducted? This week?
Okay, so at first, since I already started the... Is it showing up? Yes. Well, since I worked on the observation normalization, I thought first about, visualizing how it's actually going on in the backend.
Right.
So here is probably the... And the observation is that, well, disregarding the score at first, here we have the different observation. I think it's Hopper. There's around 15 maybe, or 13. And
wait, well, what does the debug observation number mean?
I log the non-normalized observation and the normalized observation.
Okay.
And since the observation is basically a vector, I had to break it down.
Wait, so if it's just one observation, it's just a singular number, isn't it?
Yes.
If you have a vector, how do you plot it?
Just a for loop over the vector of observation.
Do you just... Oh, I see. You're looking at the each individual element in the
yes,
observation.
Yes.
I see. Okay, I got you.
Okay. So this is what comes in. So I standardize the color, and the blue is basically no normalization. The red one is observation normalization. So here there is already something I found weird is that the default observation is actually quite stable, like well behaved, right? And the normalized one actually becomes way more, let's say, has a more wider range. So
right.
I do not know if this was the command 1 dB probably.
Yeah, I noticed recently it's doing a lot of that for whatever reason. I think it's we're probably loading too many things.
Probably. Okay. Well, so that's actually what I remarked all across the observations. So I was wondering maybe you guys will have an idea, because when you say normalization, for me, I expect it to be something more straightforward.
Right, maybe the instead of being more spread out, like what's shown in the picture, it should be more sort of in the middle. So I think the idea that this could definitely happen, I would imagine the reason why this happened was because the observation for the particular element doesn't change very much. and then when because of that, when it changes just even a little bit, it's not gonna show up like a really big change. If you just look at its values on process. However, if you do the normalization, suddenly it's saying that's a huge change from its average. That's why it's more spread out, like what's shown on your image.
Okay, I see. So maybe it's actually better for the agent because it remaps the observation information in a sense.
Right. It's learning that sometimes even small changes matter. I guess.
Interesting.
Yeah, it's a shame that your other observation debugging wouldn't load. It's pretty funny. It's probably
well, you can always access it. I made the reports and all the projects public, so.
I think recently they're trying to update their systems and it's causing a lot of issues. Like they have a update with the video. I'm not really happy with that, but it's okay.
So in general here actually, I don't know if it's luck, but the normalized observation version actually achieves a higher score, higher performance than the default one.
What about the performance in another environment?
Let me see. Actually, this is it comes next. It comes later. So and this plot was really important, but I think I had it in Slack.
So one thing you could do is to delete a couple of the plots for the observation. Maybe it'll load faster.
Maybe.
Yeah.
Maybe, right.
If you have it in Slack, that's totally fine too.
There is the picture already, so.
Right.
Yeah, it's something around this.
So it's very similar, actually.
No, in this case, it's the inverse because the green one is the normalized reward. And in this case,
I see.
You get actually expected normalization.
Right. I think in a way it makes sense because it's a normalization is saying small changes shouldn't matter, but it's also saying big changes shouldn't matter that much. Right. The small changes got enlarged and big changes got shortened or they become smaller. Right.
Yeah, so that's basically it for the debugging, and now the real runs. So regarding the normalized observation, on top of that, I also experimented with the KL bounded and KL unbounded variants. I don't know if you remember when we cut the policy update short, depending on the KL.
Right.
And, well, here with just normalized observation, we already have a boost of performance, even in the case of unbounded KL.
Right.
And it's also the same for the KL bounded, although the KL bounded has a higher performance than the unbounded. So.
Yeah, I found the KL. Yeah, I'm gonna get into the KL bounded thing later after your presentation.
Okay. But I think this actually brings us back to TRPO more or less.
Oh, really?
Because it's the TRPO that introduced the KL bounding.
Right. That makes sense.
It's not really PPO anymore. But
Right.
Next is, unfortunately, it seems I do not have normalized observation experiments on other environments. Just Hopper.
No, that's fine.
Okay. So in the case of rewards, this one is actually what gives quite a good performance improvement, but the stability is still quite bad, especially in the KL unbounded case.
Right.
As can be seen in this.
Wait, so is this the Z filter or the return filter?
This is just a Z filter.
Okay. And you have the, did you add the mean back?
The mean. No.
So the center equal to false, right?
Yes.
Okay, I see.
And no resetting also.
Okay.
And in the KL bounded case too, we have quite a significant improvement in performance. So
wow, so the KL technique really is quite general, actually.
yes, especially from the viewpoint of stability.
Right.
Once it has converged, it keeps around that optimal policy. But without the bound, it actually degenerates pretty quickly.
Right.
So this one is actually the one using the reward filter. Here the concern runs are in purple, and as you can see, it's bad, really bad. So I'll check our source code later to see what I did wrong.
Wait. Can you go back to that real quick?
Just a second. Yes.
So the blue lines, what are the blue lines again?
The blue line are always without normalization, without any tricks.
Okay, I see.
In this case, the purple one is with your reward filter.
Right. So the return So the return filter is the you don't reset it, right?
No, I didn't reset it.
Okay.
Maybe I'll try doing that next. And this one, what is this one? Oh yeah, basically battle royale between all the normalization. Well, the reward normalization, not return, right? Reward is always is what seems to give the best impact, as in the paper, if I'm not mistaken. Especially in the without KL, this one is quite pretty, if you ask me.
Yeah, for sure.
And what is the last one? Oh, actually, the yellow plot here is the combination of normalized observation and normalized rewards.
Oh, really? Okay.
It actually doesn't seem to help that much. On the contrary.
Yeah. It's interesting.
So too many cooks spoil the broth. Okay, that's the purpose.
Yeah, it's more of a lot of the trick seems to be more of an art than science at the moment.
Yes, as someone said, I think John Schulman is an empirical science for now. Right. So that's pretty much what I have regarding the normalization experiments.
Okay. Yeah, that has a lot of insight. That's great work.
No, it's just compute, basically.
Wow.
Okay. So next, I tried the learning rate annealing one.
Okay.
So regarding the implementation, I will quickly go over the corresponding code. So here, basically, I just add a toggle switch to, use anneal or not, which is then used to create. So instead of using the linear schedule as you proposed, there was actually already such a module you can.
That's perfect.
Graft to the optimizer itself, as can be seen here. So in this case, I used the lambda LR. It's actually what they used in the original work too. So here it declares is it big enough? Okay.
Yeah.
And annealing, I think that takes as input the number of time step, and will anneal the learning rate corresponding to it. So once you've done that, you just attach it to the corresponding optimizer here. And once we have the scheduler for both the policy and the value function, in the training loop, here, that's actually where I have one question, because in this case, I only anneal the learning rate once I have fully trained both the policy and the value function.
I don't think that's gonna be a huge issue, because if you do it afterwards, then the next time step, it's sort of like you're doing it beforehand for the next time step. It's just a minor -1 +1 difference. Right.
It's gonna be quite insignificant. That's also. But in any case, it's probably possible to just move this component inside the loop to have more accurate annealing, if one could say so. And as a result, actually, not much improvement.
Okay.
Not as much as in the paper, anyway.
Right.
So actually, when when not using the KL bounding in the policy update, I expected the performance to actually stabilize as the training goes further, but this was not the case. Well, that was my hypothesis.
Afterwards, I'll have a little comments about why the performance went flat in the end. I actually look into the logics. It's not related to this paper, but I'm working on the current research that I'm working on. Basically, has that exact problem that the performance just flatten out, and that's not really acceptable. And I look into the logics. It turns out the logics explode. So I don't know whether that's going to be the case with these as well. But using the KL divergence bound help a lot with that.
I see. So wait a second. Is this because of the policy then? Because here I think the log STD is a NN parameter. Maybe it's because of that. But that's also what they do.
So if you want to look into this, you have to print out the mean and log standard deviation. But let's talk about that after. Maybe see all the experiments. That way I'll be able to show you and we can discuss based on that.
Okay, no problem. So here, not much performance improvement. It's the red one is the one using the annealing, and well, it's pretty close. At some point, it reaches maximum performance, but beside that, not much improvement, unfortunately.
I see.
I think, and there does not seem to be. Okay, this one I managed to try it over multiple environments and the same observation every time. But actually, it quite bothers me now that you said it. It's always
flattened now. Yeah, I think there's a reason to that, and I don't know whether that's going to be a bug on my code part or is it more of a very common problems, but we'll see.
I see. So yes, unlike the paper, unfortunately, annealing the rate does not improve much. Let me check this really quick.
Yeah, for them the difference is quite huge. So we are only able to reproduce the normalization of rewards part. The paper
maybe it's also related to their, I don't know, the structure of their policy. Maybe.
Yeah, I don't know. Maybe.
Okay.
Like it could also be like a hyperparameters kind of thing, right? Like how fast are you doing the annealing?
No, maybe.
But that again shouldn't really be an issue.
Okay. So last one is the weight initialization, namely using the orthogonal scheme. So for this experiment, again, it's just copy pasting from their source code. They have this orthogonal init function. Actually, I didn't have the time to make sense of what it's actually doing here. But yes.
Yeah, I think PyTorch actually has a built-in orthogonal initialization method, so you don't have to do this. But that's doesn't really matter.
So this experiment just consists in changing the initialization of the policy and value function. So that's pretty much it. And as a result, while I would like to say the orthogonal initialization gives just a really slight boost at the beginning, I do not think it's something.
So it doesn't really matter as sort of shown in the paper, right?
It's even with the KL. Well, actually, in the case of the KL,
it is pretty good.
Right? Yes, it's actually not that bad.
Yeah, with the hopper bullet. Okay, I see.
Actually, it's not over yet, so maybe it's around.
I see.
500 bucks. So.
Right.
The half cheetah. Well, in the half cheetah case too, it's not that bad, especially in the beginning. And with the KL bounded version too. It's actually a little improvement, but
But then it
quite
actually
stable.
decreases performance, right? And this is with KL, and its performance dips at the end, right?
Oh yes,
Pretty hard.
for reason unknowns.
Right, for a reason unknown.
On Walker, it's a catastrophe, at least in the
Okay.
unbounded case.
Right,
Well,
right.
the KL one is usually the most stable, so
Right,
especially
right.
at this spot, we actually have quite a high score here.
Yeah, definitely.
And humanoid, the big boss, are always quite picky.
Right.
Not much.
So with the KL,
The KL version is actually worse in this case.
it's not too much worse anyway.
But that's usual because it takes more time to converge on humanoid. I noticed some other experiments.
Right, right.
And I think I'm pretty much done here.
Okay. Yeah, if you take a look at my screen, I'll share with you a little details on the issues with the logics being blown up. So one of the So if you take a look at my screen,
Yes.
did you see the reward here, and then how it just flattened out? So this is using A2C, and I was really wondering why it would just do that. And then what I did was to print out the logics, and then so this would be the action space. Imagine for this part, it's just 6 actions, and notice how it has gone from, this is basically like -1 some millions, and then when you do the probability distribution, it's always like with one action being just 1. So where's the output.log? So if you look at the beginning, this is what the logic should look like. My computer is getting a little laggy because of that. But it's like, for the most part, everything is normal. And then at some point, like this is all normal, right? You see, it's like at some point, some sort of gradient just went wrong, and then it blows up. Yeah.
See.
That's pretty interesting, right?
Saddening, but yes, interesting. Indeed.
Yeah, sadly interesting. So I think that might be the problem that's exactly happening with all of the experiments without KL divergence. And I actually did a little experiments with the KL divergence because my gut, well, based on your experiments, and my gut tells me the KL divergence seems to be really helping, and this is with KL. And then when you see the logs,
I think that there was no loss in performance, right?
yeah, no loss in performance. So notice how the logics didn't blow up anymore like it did in the beginning. It seems to be blowing up in a very slow fashion. So you see in the beginning, it's more like 0.2, 0.3, 0.2, that kind of thing. But then it seems to be not exactly be the case in the end. It's more, actually it seems to be okay. It seems to be pretty good.
Yes, it's still nothing unusual.
Yeah, nothing that really would stood out to you, you know. So the way that I implemented the KL divergence, so this is A2C, right? It's not the PPO. The way I would implement it is actually, so I would say I will perform an update, and then if the update is greater, the KL divergence of the what's being produced by the updated policy is greater to a certain limit, then I actually roll back to the previous policy. So that's a little different from what the PPO does, because PPO, what they do is they will try to push the policy, and then once they reach or get out of the target KL bound, then they just kind of stop the update, right?
Yes. So the resulting policy, it's actually already out of the trust region.
Yes,
just
yes.
a little bit. Yes.
Yeah, so
Makes sense.
My current implementation is that once you're out of the trust region, you go back. you go back to the original point. And as you can, right, you couldn't see. So I actually plot out of the approximate KL as well. You see in the beginning, the agent is able to learn a lot, but as time goes on, the KL divergence just become really huge. It's like 0.11 something. And then I think the limit is 1.5 times the target KL, which is 0.01, which effectively makes the approximate KL has to be smaller than something like 0.015, right? And this is way over it. So I think basically after 100 time steps, the agent just doesn't learn anymore. Which seems to be very consistent with what I have here. The agent's performance is just this after 100,000.
Not much change.
Yeah, not much change, because of the KL bound that I set. So a couple of ways to do it differently. First of all, I could always use like a linear schedule, some sort of optimizer that makes the gradient a lot smaller than it currently is. The other thing that I think would be really interesting for our implementation discussion is how different authors step into they use different ways to do the update, to step the game. So I don't know if you have taken a look at the OpenAI Stable Baselines library, but they have this this parameter called n steps. And then I think that's essentially the parameters that is being used in the PyTorch, PPO, A2C, Actor, Gale repository. They do similar things. So it's very interesting in the sense that the steps is usually 5, at least for the A2C. For PPO, I think they set it default to be 128. But for A2C, it's usually 5. And what that means is that you're going to, for each episode, you're kind of running the steps. You're running 5 steps. And then you're stepping into the environment with the actions, and then you store the log probabilities, the actions, and everything. And then you just update. So it's almost like you're updating the first 5 steps of the episode, and then you keep going. If you look at here, after so what they do is that they run the algorithm for 5 steps, and then they put it into the rollouts, which is the sort of like their storage engine, and then they compute the returns. And then they update the rollouts. They update the agent based on the rollouts, and then they call the after update, which essentially brings the last observation into the first observation, and also setting up some other things.
I wonder if it's enough just 5 updates per episodes.
No, well, it's doing an update per 5 steps, right?
Every 5 steps.
Yeah, so that's the more interesting part, and I think
basically a trade-off between online and offline learning in this case.
It's still online, actually. It's just the frequency at which you update the algorithms, right? But if you take a look at their code, they only do this for the observation, but they don't do that for the rewards and the log probabilities, which means the agents still have this continuous action probabilities, action log probabilities, and the discounted return. So that thing is you don't reset that. So I think that makes it possible for you to run the algorithms on sparse rewards environment.
I see.
But it's very interesting. People do it very differently. So if you think about this is basically run the updates on the first 5 steps, the second 5 steps, the third 5 steps. And one of the repo that I've looked at, they actually sample. So what they do is they take a sample So if your episode is like 1,000 time steps long, it'll sample 32 time steps and and get the corresponding advantages and policy loss at each time steps, and then optimize over that. And again, I don't really know whether that's gonna help or not. You know.
The sampling is done randomly, right?
Yes,
so
yes.
It's the same as the spin-up, I think.
Right. So, yeah, that would be a little different than what we have here. Right, because this is every 5 time steps, right?
Every 5 steps, yes. Interesting.
Yeah, I really don't know. I feel like this could be sort of something that we could investigate into as well.
But the fact that this is mostly empirical, I wonder if we can really grasp how the policy is changing with updates every 5 steps and with updates, for example, at the end of the episode.
Right. So that's very common, right? And that's basically the usual case. You update at the end of the episode, and the parameter, the num steps, is not documented in either this repository or in OpenAI. Like that, like they document it, of course, just say it's a number of steps per update, but they never really explained why they put it there or if it's important.
Yes, I see.
Yeah, I don't know. That's about what I have for this week, and
I had
go ahead.
One more question regarding the. Well, it may have some relation with the logits exploding.
Okay.
When we have the PPO, the policy used in PPO does not have any kind of squashing methods, like in Stack, for example. So. Right. Maybe if we could constrain the output to a certain range, there will not be such explosion. Just for KL to come in.
Probably, but that also works with discrete action space, right? Because in discrete action space, you're using a softmax on the produced logits, and then the problems that I was having is the logits themselves explode. So.
Oh, even in discrete case?
Yes, in discrete case. So that's the problem that I was having. The logits explode in the discrete case, and it's very interesting in that. Yeah, it's like at some point it was all normal, and at some point it just suddenly exploded. It's extremely difficult to reproduce. And it happens so randomly. It's like the agent is learning well, and all of a sudden it just went to shit.
You know you're real desperate when you reach page 4 of Google search results.
Yes, that's pretty sad. Yeah, like if you see the num steps ATC, and then there's not a lot of things to talk about, like why is it there. I hate to sort of end this. It's a really good conversation, but I actually have to run today. Does anyone have a last minute questions or comments? I maybe have another 2 minutes or so. Why don't we talk about shortly about the next steps, and I think I'll wrap up and ready to go. So is there any tricks that we haven't experimented yet?
Maybe in my case, I did not try the gradient clipping.
Yeah, that's probably a really minor issue. I think so if you look at our code, pretty much all of our code by default has the gradient clipping. I don't know if you have noticed that.
Yes, I know the torch utils or something.
Right. Yeah, I don't think that's going to cause a huge problem. It's more like something that is just there.
I think overall we've tried all the tricks they said work best. Mm-hmm. Some didn't work as well as expected.
Mm-hmm. So, go. Yeah. From your perspective, would you say the KL bound and the reward normalization seem to be the one that works the best?
The best indeed. And the KL bound is actually, is it in the paper?
I don't think so, actually. Yeah, in the
Maybe
paper.
that's called PPO plus.
Yeah, I don't know. But yeah, that's interesting. What about the observation normalization? Sometimes it works, right?
Yeah, sometimes it works. I think it works quite well on 3 out of 4 environments I tested on.
Okay, I see. So maybe those 3 techniques will be the main one that we can add. We should consider adding to the repository. All right, I have to run. But if you have anything, hit me up on Slack. Send me a message or something, and then we can discuss. And thanks everyone for coming. And I hope you have a good weekend.
Likewise.
All right, thank you. All right, bye.
See you.